Welcome again to my classroom. Continuing with the topic of soil architecture, today we will study characterization of soil structure. Soils, aggregates could be characterized, or I should better say could be classified on the basis of their shape, on the basis of their size, and on the basis of their strength. So, you may have on the basis of shape different types of aggregates like platy, angular, subangular, blocky, spheroidal, that depends upon the shape of aggregates. Then size of aggregates, you may have smaller aggregates, micro aggregates, domain, macro aggregates, something like that. And based on their strength, you have moderately strong aggregates, weak aggregates, very strong aggregates, something. But the question is, I as a soil scientist will be more interested to find out the stability of aggregates and at the same time the stable aggregates of different sizes. This is very important for me because my soil may have dominance of macro aggregates. Some other soil in another land use may have dominance of micro aggregates, macro aggregates, or in between size, whatever it is. So, the question is that under what land use macro aggregates are dominant, under what in another land use micro aggregates are dominant. So, for these studies we should have a knowledge about the stability of different sized aggregates in a particular soil, what we call as characterization of soil structure. So, we can characterize soil structure on the two bases. One is dry sieving, because when you have to go for different size of aggregates, you have to sieve the aggregates so as to separate different types of aggregates. In dry sieving, what we do is that we have a nest of sieves, different sieve sizes. Say, first of all, we could have the sieve of 2 millimeter, followed by 1 millimeter, then followed by 0.5 millimeter, followed by 0.1 millimeter, or let it be 0.25 millimeter. Then you could have 0.1 millimeter, and this is simply a pan. So, what we do is that we place our soil sample over here in the topmost sieve, and we have a rotary sieve shaker. So, we shake this nest of sieves say for 30 minutes or so, and then there is friction, and aggregates may get broken down, and after breaking down the aggregates could be retained in different sizes of the sieves, and then you can separate the aggregates from different sieves. So, whatever aggregates are retained on this sieve, topmost sieve, we call this as aggregates more than 2 millimeter. Then whatever is retained over here, 1 millimeter sieve, we call 1, between 2, then 0.5 to 1, so on, and ultimately this pan may have the aggregates smaller than 0.1 millimeter. So, this is how you simply after dry sieving you can find out the distribution of aggregates. But the question is, under realistic situation, our soils are seldom dry. This is only applicable where you have to study the wind erosion, because wind erosion occurs under dry land conditions, or I should say better, dry conditions. But for most of the time our agriculture lands, agriculture soils are basically moist, could be wet also sometimes, and at the same time when rainfall is there, rainfall may have two type of action. One is rainfall directly strikes the aggregates and breaks down into because of its kinetic energy, and second is when these aggregates are wetted by the runoff water, again the aggregates may get destabilize and get broken down into more stable aggregates. So, for that we go for another process what we call as wet sieving. Now, in wet sieving again we have this type of nest of sieves, and this nest of sieves is then shaken vertically up and down. This is your nest of sieves. So, this is all filled with water up to this level, up to the level of topmost sieve. So, what we do that in both the cases, whether it is dry sieving or wet sieving, we take the aggregates, sample of aggregates, or better you call soil sample for aggregate size analysis, which is passed through 8 millimeter sieve. This is 8 millimeter sieve, and then we have a 4 millimeter sieve. So, the aggregates which pass through 8 millimeter are retained on this 4 millimeter sieve. So, this is your sample for analysis. So, first of all, what you have to do now, for example, you are asked to go for aggregate size analysis. It is very important that when you collect the sample from the field, it is always better to collect a bigger clod. I mean, which is easily picked up. Either if it is visible, you can pick it up. If it not, you can take a spade and take out a bigger clod, because that bigger clod is not in fact the realistic representation of aggregation. Then simply you go to a grassed land, grassed soil, and let this bigger clod fall from your hands. You don't have to throw it down, just let it fall down. So, what will happen when it will fall on a grassy land? It will break down. It will break down from certain points of weakness, or what we call as points of cleavage. So, once these aggregates are broken, there may be a mass of bigger, smaller aggregates. You take this sample, dry it in the oven for 24 hours. After that, you take some sample, pass it through 8 millimeter sieve, and then whatever is retained on 4 millimeter sieve, that will be your sample. So, you have to take 50 gram of this sample and place it on this topmost sieve. So, next precaution is that after you place this on the topmost sieve, it is not that immediately you start shaking, because when it will be immediately dipped in water, the air inside the aggregates will try to rush out. When it will rush out, it will cause a micro explosion. So, air explosion needs to be avoided. So, otherwise, because when air explosion will be there will be breakdown of aggregate, and that will not be because of wet sieving, but it will be because of the rushing out of the air. So, in order to avoid that, what we do is that we place the sample over here, and before placing the sample, we wet this sample through the process of capillarity. So, this is another step. Wet the sample through capillary process, so that you have sufficient time for the air to come out of the aggregate. Once this sample is wetted, only then you have to place this sample over here. So, I should say it is now pre-wetted sample. So, pre-wetted sample is placed, and then we go for shaking for 30 minutes, and it will be up and down shape, not the rotary motion as in case of dry sieving. It is up and down shaking underwater. Now, what will happen that after wetting, the aggregates, some of the cementing agents, particularly the temporary and transient cementing agents, they will dissolve. The aggregates could broken down in different sizes and retained on each sieve. So, after 30 minutes, you take this nest of sieves out of water, dry it in the oven for 24 hours, then weigh the material retained on each sieve. So, now you will have weight of soil material or soil mass on each sieve. So, let it be WDI. I is on ith sieve. So, weight of dry mass on ith sieve. This sieve could be 2 millimeter, 1 millimeter, 0.5 or whatever it is. Now, the next question is whether this soil mass are these aggregates. This is a big question mark over here. These could be aggregates, these could also be primary particles. But at least for the first sieve, that means 2 millimeter, you are sure that these are aggregates. Why? Because primary particles cannot be smaller than 2 millimeters. So, first sieve, or you say 2 millimeter sieve, we can say yes, these are aggregates. Other sieves, you can say either yes or no. So, the question is no, because we are not sure. In first case, we are sure. Now, since we are not sure here, then what is the next step? Next step is that you go for dispersion of soil mass. Dispersion of soil mass on each sieve, except the first one. So, whatever material is there, you take it in a beaker, 500 ml beaker, then you add some hydrogen peroxide, then remove the cementing agents. You have to repeat the same process as we discussed in mechanical analysis of soils. So, once your soil is dispersed, you have added this sodium hydroxide or sodium bicarbonate so as to disperse the soil particles. Then you have to pass this dispersed material, pass dispersed material through the same sieve from which you had taken it, through the same sieve. Now, if nothing remains over here, this is very important, if nothing remains over here after dispersion, then that means whatever you had. So, if I say if nothing retained, then your mass of aggregates will be this. This will become mass of aggregates. Now, you can say yes, this is the weight of aggregates. But if something remains over here, then you have to subtract it. Otherwise, let me rub it. So, if some material, and this will be mostly sand, because this is all relates to sand size, is retained, then dry it and weigh it. You have to oven dry it, weigh it, and then weight of aggregates will be equal to weight of dry mass of soil, let it be I over here also, minus, so weigh it after weighing, say it is WS, weight of sand, and on ith sieve, so WS minus I. This is what we want. This is actually, now we are sure this is weight of aggregate retained on sieve. So, this could be 1 to 2 millimeter aggregates, 0.5 to 1 millimeter, 0.25 to 5, similarly less than 0.1 millimeter. So, ultimately, now you have this type of, first of all, you have sieve of 2 millimeter. So, better now you call it as more than 2 millimeter. So, sieve, or better, aggregate size. Okay. Then 1 to 2, then 0.5 to 1, then 0.25 to 0.5, then 0.1 to 0.25, then less than 0.1 millimeter. Okay. Then against this you have weight of aggregate. So, over here say it is W1, W2, W3, W4, W5, W6. Then you have the mean size. This is again in millimeter. This is sieve size, mean sieve size. Now, mean of this and this is quite clear, 1 plus 2 divided by 2, so 1.5. Similarly, this, all this. Now, what about this, more than 2? How to find out the mean? If you remember, we had taken the soil sample as passing through 8, retained on 4. So, passing through 8, kept on 2. So, 8 plus 2 divided by 2, this will be 5. What about this, less than 1? So, less than 1 could be the lowest limit is 0. So, 0 plus 0.1 divided by 2, 0.05 millimeter. This is how to find out the mean. Now, the first thing is that you want the distribution, you can find out the percent aggregates. So, percent aggregates. So, not weight, it is percent aggregate of each size. So, this could be P1. So, P1 is now W1 divided by 50, because we have taken 50 gram of the sample, multiplied by 100. So, this will be P1, P2, like this, P6. That is all. You have found out now the percent aggregates, percent water stable aggregates of each size. Now, the question is, when you have to compare the two samples, sample 1, sample 2. In one sample, a particular size could be dominant, in another soil sample, another category could be dominant. So, it is very difficult to compare the two samples with 6 values. So, until and unless you have one value, you cannot compare the two samples. Now, for going for one value, now what we do is that we take weight of aggregates in multiplied by the mean sieve size. Okay. So, let it be that it is MW1, MW2 and ultimately MW6. So, then you take summation, add over here on I to 1, I is I 1 to 6, I is equal to 1 to 6. So, when you add it up, so this means summation of I 1 to 6, what you have added? Weight of aggregate in ith sieve multiplied by mean sieve size of that particular category divided by the weight of the sample 1 to 6, that is W. So, this is basically, this is here 50 grams. So, so this will be mean weight diameter, and properly we call it as MWD. So, this will be in millimeters. Now, you have one value MWD. Now, you can compare maybe hundreds of samples, that okay, the highest the mean weight diameter, more stable will be the aggregates. Simple. Sometimes instead of mean weight diameter, we take the geometric mean diameter. In geometric mean diameter, what we do is that instead of taking this sieve size, we take log of this sieve size, log xi, and this log of xi is multiplied by weight of aggregates, I should say it is log of xi. So, in this case geometric mean diameter, again in millimeters, this will be the exponential value of summation of I is equal to 1 to 6. So, W aggregates, so you can say log of xi multiplied by weight of aggregate divided by simply y to 6. So, take exponential value of it, this will be geometric mean diameter. So, this is second, in these are basically indices of characterization, indices for characterization of soil structure. So, first index is mean weight diameter, another is geometric mean diameter. Just now I talked that we are interested to find out the impact of the water drops, raindrops in affecting the structure of the soil. Now, here you are simply shaking under water. So, what about the kinetic energy of the raindrops? So, here what we can do is that you can again take a sand bath. This is your sand bath, and you have placed a pre-wetted aggregate. Again, this is your pre-wetted aggregate, and then we try to simulate. This is simulated raindrop, falling from a height of 2 to 3 meters, because when a raindrop of say 1 millimeter, 2 millimeter up to 2.5 millimeter, it falls from this height, it achieves around 80 to 90% of its terminal velocity. So, it is very important that this drop is falling with a terminal velocity. Terminal velocity means when there is no more acceleration due to gravity acting on this raindrop. It is not accelerating, its velocity is not accelerating, that is called terminal velocity. So, this drop is then led to fall on this aggregate, and till the aggregate disperses completely. So, we have to count the number of raindrops used for complete dispersion of the aggregate, and then we can frame a this is stability index. So, this stability index called SI, it was developed in PAU by Professor Kuckel and his team. We call this as SI. So, this is number of raindrops multiplied by 1/2 of mv square. M is mass of raindrop, because we know the volume, we can find out the mass, we know the terminal velocity, and we can find out stability index. Higher the stability index means more stable aggregate under the impact of raindrop. So, apart from mean weight diameter, geometric mean diameter, we can have stability index. These are 3 indices of characterizing soil structure. So, I hope the things are clear. Thank you very much.